Having proved that the equation for the parabola passing through the origin and with focus and directrix as shown is y squared equal 4ax, we now go on and look at some of the basic properties of the parabola, which can be determined by just looking at the equation of the path. So on this diagram we see quite a lot of information shown. In particular, what it tells us, for example, is that for a fixed value of x, say x equal h, by substituting that into y squared is 4ax, we get two values for y which are plus or minus the square root of 4ah. In other words, for every fixed value of x, there are two corresponding values of y on the parabola. However, for a fixed value y equal k, then that only gives one value of x, which is k squared over 4a, as shown here. So in those two cases, I've just labelled the one point here, where you're given the y value, and this is the x value, whereas for these 2 points, given the x value, there are 2 points y. Equally, one can see that by replacing y by minus y in this expression, then the equation is still satisfied, which means that for every point xy on the parabola, the point x minus y also satisfies the equation. In other words, the parabola is symmetric about the x-axis, y equals 0. We also see that because we've taken a as positive, then because y squared will always be greater than or equal to 0, then x must always be greater than or equal to 0. In other words, the parabola must lie to the right of the origin and the y-axis, except there's the one point where it actually passes through the origin. Finally, we can determine at any point P on the parabola the gradient of the tangent at that point simply by either rearranging y squared is 4ax by writing y equal plus or minus the square root of 4ax and differentiate to find the gradient of the tangent, so the gradient of the curve at that point, or more simply just implicitly differentiating this expression, we get 2y dy by dx is 4a. In other words, dy by dx is 2a over y. So as shown here, at any point p, x, y on the parabola, the gradient of the tangent at that point is given by 2a over y, which we can obviously rewrite in terms of x by using this expression here. So as you see, there's a summary at the top here that tells us all of that information, and in particular we notice that because y squared is equal to 4ax, as x gets larger, y gets larger, so this parabola does not approach an asymptote. So it doesn't approach a fixed horizontal, vertical or other line as x gets bigger, y gets bigger. At a slower rate, we know that the gradient 2a over y, as y increases, this gradient will decrease, but nevertheless is always positive for finite x, and so the graph just continues on forever. So as you can see at the top there, implicitly differentiating the expression here, the Cartesian equation for the locus, we get dy by dx is 2a over y. Now, all parabolas look the same in the sense that if you change the focus and directrix move one away from the other, in other words, you change the value of A, then all that happens is that this curve either opens out or closes up. So for example, if we take another parabola, y squared equal 4bx, for a value b which is not the same as A, which will have a focus at b comma 0 and directrix at x equal minus b, we can, by multiplying this expression through by a suitable ratio of A over B, obtain this equation. This is exactly equivalent to this. You can check that by multiplying it out. And what this looks like, of course, is some number squared, some coordinate squared. It's 4A now times another coordinate, another number. In other words, if we replace this y coordinate by a stretched coordinate called capital Y, which is just related to little y through this, and similarly x being a stretched coordinate, which is the x coordinate multiplied by A over B, then we get now capital Y squared is 4A capital X, where x and x upper and lower case are related in exactly the same way that y is related. So this parabola and this parabola will look very similar to one another, but where we've stretched the x and y coordinates. In other words, if you were to draw the parabola on a piece of rubber and stretch it horizontally and vertically, any parabola can be made to look like any other parabola. Now, one of the most difficult things that we're going to do now, but what makes life a lot easier for us later on, is to determine the parametric form for the equation of a parabola.